Hello, dear students. In this chapter, we want to start the concept of Markov decision processes. As you remember, in the queuing theory chapter, we just mentioned about this topic a little bit and the property of Markov. In this chapter, we want to talk more about this item, reviewing some examples. We start this chapter with an introduction, then we follow a prototype example and talk about the different characteristics of a Markovian problem. After that, it's the time to present a model and a standard model for Markov decision processes. Then through linear programming and optimal policies, we review again the concept of Markovian, but from the other point of view. And finally, we conclude this chapter with a brief conclusion. A Markov process is a stochastic process. What is the meaning of a stochastic process? Is a process that evolves over time in a probabilistic manner. As you remember, in the chapter of queuing system, as I described, there are many of them a stochastic process because, for example, the number of customers in the system evolves over time in a probabilistic manner based on the uncertainty about when arrivals will occur and how long the service times will be. As you remember, guys, in the queuing theory chapter, I just told you, based on our observation, we find the distribution and we find the probability of the arriving and the service. And because we live in an uncertain world, the majority of the cases that follow this uncertainty, and obviously they have this stochastic form. Besides, as maybe in the previous, in the TACO subject you learned, the inventory management as well evolves over time in a probabilistic manner based on the uncertainty about future demands. So we named this item as Markovian property. Based on this reason, Markov chains are a particular important type of stochastic process. Markov chains have the special property that probabilities involving how the process will evolve in the future depend only on the current state of the process and so are independent of events in the past. As you remember, the model of birth and death that we described in chapter of queuing theory fits this definition, as do all the queuing system we described in the section 17.6. If you don't remember, please review the presentation of the queuing theory, and they are based on the birth and death model. So the lack of memory property is referred to as the Markovian property. So again, I repeat, the situation of the future, it only depends on the current state, like the birth and death model and all the models based on birth and death. And besides, as you remember, I gave you the example of a drunk man. Okay, so each time a Markov chain is observed, it can be in any of a number of states. It can be continuous when a continuous time Markov chain is observed, whereas a discrete time Markov chain is observed only at discrete points in time. Okay, let's continue. So the transition matrix gives probabilities for what the state will be next time. It means that moving from the current time to the upcoming time, and these connections are the probabilities of changing the current state to another upcoming state. Many important systems can be modeled as a discrete time or continuous time Markov chain. In this chapter, only we focus on how to design a discrete time Markov chain for optimal performance. Let's review our prototype example. A manufacturer has one key machine at the core of one of its production processes. Because of heavy use, the machine deteriorates rapidly in both quality and output. Therefore, at the end of each week, a thorough inspection is done that results in classifying the condition of machine into one of four possible states. So as you see here, guys, end of week inspection classifies states are four states. State 0, that means good as new. State 1, it's one state after 0, operable but with minor deterioration. So for sure the output is not ideal, but it's somehow acceptable. State 2 is operable. Again, the machine works, but the problem is more serious. And the state 3 is when the machine is inoperable, that output of unacceptable quality. So for sure, these states could be the states of the current week or the state of the next week based on the Markovian property. It means that when we make a comparison between what we finish of this week, that can be one of these items, and what we have in our next week, that again are these four states. So the machine, the states of the machine are not out of these states. Let's continue our prototype example. After historical data and this inspection results are gathered, statistical analysis is done on how the state of the machine evolves from week, the current week, to the following week, week to week. The following matrix shows the relative frequency, the probabilities, okay, of each possible transition from the state in 1 week, okay, one of these states possible, to the following week. Again, one of these following states. As you see here, to explain this item, in statistical analysis has found that these transition probabilities are unaffected by also considering what the states were in prior weeks. So it means that there is no relation with the states what were they were in past. So what is this property that we learned before? Is a Markovian property. That was the lack of memory that characterize Markov chains. Therefore, letting the random variable xt be the state of the machine at the end of week t, the conclusion is that the stochastic process is a discrete time Markov chain whose transition matrix is just the matrix that we have here. Let's review the elements of this matrix. What are the meaning of that? It means that, for example, if at the end of the current week we are in the state 0, with the probability of 0, we will remain in state 0. With the probability of 7 divided by 8, we go to the state 1. With a probability of 1 divided by 16, 0 will be changed to 2, and with the probability of 1 divided by 16, 0 will change to 3. And obviously, all of these probabilities are equal to 1. Again, this one. When after the inspection of the weekend, we see that the machine is in the state 1, it is impossible to go to state 0, it means improvement, without any action. In our next table, we'll see some changes. But at this moment, we'll see it's not possible. When we are in 1, with the probability of 3/4, we remain at the state 1 with the probability of 1/8, and 1/8 will go to the state 2 and 3. Guys, check here that each of these states, if they grow, it means that the worsen of the situation of the machine. The same happens when we are in state 2. It's not possible to go to state 0 or 1 that are better situations without any action, but it says with a 50% and 50%, it remains in state 2 and state 3. If the machine is in state 3, as we remember, it was inoperable, okay? What will happen in the end of the next week is only the situation of 3 that is inoperable, that the machine doesn't work. So we'll see that we should do some actions to continue the processing of the machine and working it. In next slide, we'll talk more about this concept. As you saw in the last row of the previous matrix, the transition matrix of the previous slide, once the machine becomes inoperable, that enters in state 3, it remains inoperable. For this reason, we had the probability of this week 3 and the next week 3 was 1. In other words, state 3 is what it's called an absorbing state. Leaving the machine in this state would be intolerable, since this would shut down the production process, because we don't have any machine to continue the process, okay? So we should do something. So the machine should be replaced. Guys, in this case, repair is not feasible in this state. When we are in state 3, repair is not feasible. We'll see in the next part that in some cases repair is possible. But when we are in the third state, the only solution is replacing the machine must be replaced. The replacement process takes 1 week to complete, so that production is lost for this period. So, as you see here, the replacement takes 1 week to complete. So, the cost of losing the profit of 1 week production is $2,000, and the cost of replacement is $4,000. So the total incurred whenever the current machine enters state 3 is $6,000. Let's continue. So, besides the cost of replacement and losing the production, even before the machine reaches state 3, it means that in state 0 or 1 or 2, costs may be incurred from the production of defective items. So it's obvious when machine is in state 0 because it's good as new, as we reviewed before, there is no infection and there is no defection, and there is no bad quality of the production. But in the state 1 and state 2, because they have problem in operation that are minor deterioration and major deterioration, the costs are $1,000 and $3,000. So these are the other costs that may happen during the production before going to the state 3. On the previous slide, we have mentioned all the relevant costs associated with one particular maintenance policy. Replace the machine when it becomes inoperable, but do not maintenance otherwise. Under this policy, the evolution of the state of the system still is a Markovian chain, but with one small change. As you see here, guys, when we arrive to this, better saying, when the machine arrives to this state 3, the only possible solution was replacement of the machine. So as you remember, when we replace, it means that a new machine. So this state of the machine in the next week is 0. Is 0. And it's the only possible state because when we start the next week, the machine is totally new and it's the only possible probability. The other items still are the same that we had in our first matrix. So I repeat, when we arrive to this part, there is not any solution but replacing the machine. Replacing the machine with a new one, it changes the state in the next week in 0. Okay, it means that good as new. So the probability here is 1 and the other probabilities are 0. So let's continue our tables. To evaluate the maintenance policy, we should consider both the immediate cost incurred over the coming week and the subsequent costs that results from having the system evolve in this way. A widely used measure of performance for Markov chains is the expected average cost per unit time. To calculate this measure, we first derive the steady state probabilities that are P0, P1, P2, and P3 for this Markov chain. This is done by writing each of these states probabilities as the sum of the probabilities of all the possible ways to transition into the state in one step and then solving the resulting system of steady state equations. So what are the meaning of all of these items? In our tables that we had, these items in the left hand side are the situations in the coming weeks, and these items this side, okay, these 4 equations, the first 4 equations, this one, this one, and this one, it says what with the what combination this probability of next week happens. After seeing that with a replacement in state 3, as you see in our table, all the current states are the probabilities of current state of 0, but the state 3 is 1. So P3 is P is equal to P0 is equal to P3. Upcoming probability P1 comes from 7 divided by 8 P0 plus 3 divided by 4 P1 of the current situation. The same happens for P2 and P3. Don't make a mistake. I extracted all these items from the matrix, the transition matrix that we have. And obviously, we know all these steady state probabilities are equal to 1. If based on the equations and relationships that we have here, I solve these items, I can find P0, P1, and P2 and P3 with these values that are 2 divided by 13, 7 divided by 13, 2 divided by 13, and finally 2 divided by 13. These are the steady state probabilities. Again, it means that if in the upcoming week I am in each of these ones, from what probability of states they are coming. Based on our table, this right-hand side is calculable. Let's continue. Let's add some new items to this example. However, there also are other maintenance policies perhaps that we should be considered and compared with the decision of we calculated before. Okay, so for example, perhaps the machine should be replaced before it reaches state 3. As you remember, we just changed and replaced the machine with a new one only at the state 3, but it says that it's possible to replace the machine when we are in state 1 or 2. In state 0 is not possible because it's new and it's not logical to change the machine, a new one with a new one. Okay, or another alternative is to overhaul, okay, the machine at the cost of 2,000, okay, that is repairing, maintaining. This option is not feasible in state 3. Why? Obviously, because when we arrive to state 3, the machine is inoperable and the only policy is replacement. It's not feasible in state 3 and does not improve the machine while in state 0 or 1. So it is of interest only in state 2. So this overhaul is only possible in state 2. A week is required. So another consensus is 2,000 is lost in lost profit from lost production. So when we use the overhaul, the machine will return to state 1, okay? So when we are in state 2 that we discussed, overhauling is one policy that changes the state of machine to state 1. But before continuing, let's focus on this calculation here, guys. Based on what we calculated before, for P0, P1, P2, and P3, that were 2/13, 7/13, 2/13, and 2/13, okay? And based on the cost that we learned, okay, $1,000 for cost of defective items in the state 1, 3,000 of the cost of defective items in state 2, and 6,000, that was the total of 2,000 for losing the production and 4,000 for the replacement. Totally is 25,000 divided by 13, that is 1,923.0.8. So the cost of doing nothing maintenance policy, expected average cost per week for this is 1,923.08. So we did not anything, and after reaching this point we just replace that. Okay, so its totally is 1,922. But besides, as we saw here, we have different other possibilities. It means that instead of doing nothing in state, for example, 1 or 2, we had other possibilities, okay, other decisions that were, for example, replacing for 1 or overhauling for 2 or replacing for 2. The combination of this will give us another cost that we want to make a comparison. And the objective here is to find and to select the minimum cost that these combination of policies that will give us. In the next slide, in 2 tables, I will wrap this explanation up. So, as you see here, to wrap up what we reviewed in our prototype example, we have the costs related to each of these states. If I select do nothing, it is possible in only states 0, 1, and 2. Why? I repeat. Do nothing is not possible in state 3, because in state 3, if we do nothing, the production will finish, but we don't want to finish the production. So the cost related, that expected cost due to producing defective items in state 0 is 0, because the machine is new and there is no defective item. Nothing of maintenance cost and nothing of cost of losing production, so the total cost is 0. If we do nothing, we just learn there is only 1,000 related to the producing defective items is 1,000, or 3,000 in the state of 2. But we just learned there is one other policy that we can select it only in state 2, that was maintenance, okay? The maintenance was 2,000. But again, when we do the maintenance, there is 2,000 of losing the production, because it means that it's waiting up to finishing the maintenance, that is 4,000. And another policy that is possible in state 1, 2, and 3, based on what example told us, the related costs as we reviewed are 4,000 as maintenance cost, and 2,000 is the cost of losing production. For sure, this 4,000 as maintenance cost is the replacement. So if we name these decisions 1, 2, and 3, do nothing, overhaul in the second state, that returns system to state 1, and replacement wherever we are return state to system, The possible relevant states are 0, 1, 2 for the first decision, 2 for the second decision, and 1, 2, 3 for the third decision. In the next part of this chapter, we dedicate our efforts to solve and find the optimal total cost based on the combination of these decisions. In this part of this chapter, we review a model for Markov decision processes to find the different policies that are combinations of the different decisions that we reviewed in the previous part, to find with which policy will have the minimum total cost. The model for the Markov decision processes considered in this chapter can be summarized as follows. The state I of a discrete time Markov chain is observed after each transition, where the possible states are I equal to 0, 1, 2 up to capital M. So these are the different states. In our case, there were states 0, 1, 2, and 3. A decision small k is chosen from a set of capital possible k decisions. Obviously, it's a combination from 1, 2 to capital K. So in our case, we had 3 different decisions. Decision 1, do nothing. Decision 2, overhaul. And decision 3 was replacement. If decision di is equal to k is made in state I and immediate cost is incurred that has an expected value of Cik. It means that the cost of taking decision k in state I. That's, for example, the cost of do nothing in state 2. The decision of overhaul in state 2, the decision of replacement in state 1. All these costs are reflected in the previous table 19.1. Let's continue these steps in the next slide. The decision of the state I, that is one of those Ks, in state I determines what the transition probabilities will be for the next transition from state I. Guys, if we name the state of the next week, we need another letter for that. So, for example, if we name the state of the next week as J, so this probability is Pij of decision K, okay? Pij of decision K, something like this. Pij of decision K, okay? That's obviously it's for J equal to 0, 1, 2, to M. Why? Because they are exactly the same states. Remember the table, the horizontal part of the table that we had. A specification of decisions for the respective states D0, D1 to Dm prescribes a policy for the Markov decision process. So, based on the different decisions that we can make, for example, for state 2, we can make 3 different decisions. For state 1, we can make 2 different decisions, okay? So, a combination of these decisions that are decision or 1 or 0 or 1 or 2 or 2m, the combination of this lets see that they will give us the different policies. In our next slides, we'll see what are these possible policies, and the objective is to find an optimal policy according to some cost criterion. Minimize expected average cost per unit time, as we reviewed before. So I repeat, here the objective is finding the minimum cost among the different policies. In our previous slides, we just found the cost of one of our policies. That was do nothing in state 0, do nothing in state 1, do nothing in state 2, and replacement in state 3. As you remember, the cost there was 1,923.08. In the other policies, we want to find the cost, the total cost, and make a comparison with this cost of 1,019 something. Let's see what are the different steps to solve that and find the solution. Our description of a policy that I told you that is a combination of the decisions for different states implies two convenient properties that we will assume throughout this chapter. One property is that a policy is stationary. That means whenever the system is in state I, the rule for making the decision is always the same. The second property is that a policy is deterministic. Means whenever the system is in state I, the rule for making the decision definitely chooses one particular decision, and it's not like a range of the amounts. So with these definitions, we are ready to solve and find the different policies. With this general framework, we'll return to the prototype example and find the optimal policy by enumerating and comparing all the relevant policies that I told you in the previous slide. Let's check our next slide. Based on what we learned in the previous slides, in this table, we have all the possible policies that are based on the different decisions. Let's review them. The first policy, we name it RA. We'll name the policies which are, and DIR denotes the corresponding decision to be made in state I, state 0, state 1, state 2, or state 3. Okay, and these are the policies RA, RB, RC, RD. They are the combination of the decisions that we can make for each of the states. So the different policies are, for example, the policy A is, as you remember, is the policy that we had in our table, no? That the cost was 1,923.08. So what are them? The first policy is do nothing, do nothing, do nothing, and replace in the third state. The other one is replace in third state, okay? That is the third decision, and overhaul in state 2. What was this decision? This decision moves the machine to state 1. In the next slides, we'll see them. The third decision is, policy is taking decision of replacing in state 2 and 3 and do nothing in state 1 and 0 and 1. As you see here, 1, 1, that means do nothing, and 3, 3 means replacement. And replacing in states 2, 1, 2, and 3. These decisions, and do nothing in state 0. So these are four different policies. No, these policies are A, RB, and RC and RD. That for each of them, obviously, we have one related total cost. Here we learn that this first is 1,923.08. Let's check what are the other costs for this different other policies based on the table we had before, table 19.1, and make this comparison and make the final decision. These four transition metrics that you see in this slide are the transition metrics for our four policies A, B, and C, and D. That we know each policy is a combination of the decisions that we'll take for our policies at the end of for our states, sorry, at the end of the current state. This slide, this table, the first one, is the table of the policy of doing nothing in a state 0, 1, and 2 and replacing in a state 3. As you see here and as we saw before, if we replace the machine, the state at the next week will be state 0. The policy B is replacing in state 3 and overhaul in state 2 and do nothing in state 0 and 1. So it remains unchanged, but if we do overhaul in state 2, as you remember, the machine next week changes to state 1 and replacing in state 3, the machine goes to state 0 and it will be as good as new. The third policy is replacing in state 2 and 3. Replacing in state 2 and 3, as you see here, it's this and do nothing in 0 and 1. And finally, the last policy is replacing in states 1, 2, and 3 and do nothing in state 0. As you see here, these three ones means by replacing the machine, regardless it is in in state 1, 2, or 3, it goes to state 0. That means the machine changed to as good as new. Let's continue this concept in the next slides. As you remember, for our first policy that we had, I told you, and for all of the policies, we need to calculate the expected average cost per unit time that we show it with EC. That is the multiplication of the cost of making decision K in state I with that probability of state I. These costs CIKs can be find in the table 19.1 all of the costs related to the different states. As you remember, for decision 1 that was doing nothing, it was possible to make this decision in state 1, 1 and 2. And the related cost was 0, 1,000, what was that 1,000 for defective items, and 3,000 for defective items. So the decision 2 was overhaul. You remember it was totally $4,000. That was 2,000 for maintenance and for 2,000 for losing the production, totally 4. And decision 3 that was replacing, that was possible for state 1, 2, and 3 was $6,000. That was 2,000 for losing the production and 4,000 for the cost of replacement. The totally is $6,000. So based on the different decisions and the decisions that are in one policy, now it's the time to calculate the different costs of policies, the expected average cost per unit time of each of policy. But we have our CIK. What remains? PI. How can we find them? In the next slide, I will explain to you. But it's exactly like the other policy that we calculated it. Let's review it. Where K is equal to di of R for each I and P0, P1 to Pm represent the steady state distribution of the state of the system under the policy are being evaluated. After P0, P1 to Pm are solved for under each of the four policies, the calculation of EC is as summarized here that we have in our table. As you see here, guys, these are the different decisions that we make in our policies, okay, and the probabilities that we calculate. As you remember, for finding this part, it's only we should make the equations of the state of the next week to find based on what elements that they can be find. So, for example, you need to write, as you remember here, P0 was equal to P3. P1 was equal to 7 divided by 8. P0 plus 3 divided by 4. P1 and the rest. You will have 4 equations based on P0, P1, P2, and P3, plus another equation that is total of the probabilities P0 plus P1 plus P2 plus P3 is equal to 1. By finding this, you are able to find all these P0, P1, P2, and P3 for all of the policies. As you see, these distributions and these probabilities are calculated here. And now we have our PI and we have our CIK. The summation of the multiplication of these items will give us our EC. As you see here, we calculate for all of this. We calculated for all of these policies, okay, that it gives us different ECs. For example, the first one is 1923, the second one is 1667, the third one is 727, and the last one is 3000. How can they calculate? Easily? As you see here, for example, for the last one is a policy of doing nothing in the state 0 and replacement in state 1, 2, and 3. We know the cost of replacement is 6. So these 6s multiplying by 14, 1 and 1 are coming from this part. So as you see here, the policy B is the best policy for our example because is the minimum. It means that doing nothing in the first one, doing nothing in the second one, overhaul in the state 2, and replacing in state